Good afternoon and welcome to our Live Lab Learning Series. We thank you for joining us. This presentation is being recorded, so you will have the capability to access and view it at a later date. For more information on our series, please feel free to go to livelablearning.com, where you'll be able to see upcoming webinars and future events for your review and participation. Today's session is on Scan-to-BIM and how it's being used today by the AEC community. My name is Robert Bloom, and I'm with Applied Software Construction Technology Group. Our speaker today is John Russo, the President and CEO of Architectural Resource Consultants. ARC is based in Irvine, California, and is an early adopter of high-definition survey technology, which is more commonly known as 3D laser scanning. Along with scanning, ARC has been a long-time provider of modeling services with specialization in building information modeling. As a GSA IDIQ holder, ARC serves both federal agencies as well as AECs throughout the country. We've allotted an hour for this overview on the Scan-to-BIM process, and should you have any questions during the presentation, please feel free to enter them in the question window below, and we will address them at the conclusion of this program. Again, we thank you for taking time today to join us, and with that, I'll turn it over to John Russo with ARC. John?
Great, thanks, Robert. I'm going to get my screen up here real quick. If you can just confirm you can see my screen all right?
We are good.
All right, thank you. Thank you, Robert. Thank you, everyone. Quick thank you out to Applied Software for hosting this session today. As Robert mentioned, my name is John Russo. I'm with Architectural Resource Consultants, ARC. And today's session is on Scan-to-BIM and how it's being used by today's AECs. So I'm going to go over quickly what we're going to be looking at. We're going to be looking at Scan-to-BIM, the process. Just kind of, if you're not familiar with or you haven't seen the process, we're going to walk away today with a little bit more knowledge on how all this works. We're also going to see some real-world examples of how scanning is being used and implemented on projects by architects, engineers, and contractors. And then we'll wrap up with a look at some other imagery, 360-degree imagery that is often goes hand in hand with the laser scan data that we generate. So first question is, if you've ever tried to document a building, you may feel like this gentleman here. You start at one side of the building, try and work your way around measuring it, and can't quite get your building to close. Well, it's a common struggle, and it just means there's a control issue in your measurements. So the first thing I want to look at today is there's different methods of laser scanning. There's what we call static laser scanning, where we set up a scanner on a tripod such as this, and it is in a static position, and it'll take a scan, and it looks like what you see on the right-hand side of the screen. And we call that a point cloud. That's just raw scan data as the scanner captures it. And it's millions and millions of data points, and each data point has an XYZ value to it, so it knows precisely where it's at in relation to the next point, and it's an actual 3D image. You can think of these as kind of like a 3D camera. The scanners can also be mounted on a vehicle and driven down the roadway at roadway speeds and capture data. These are as an example of an exterior mobile scanner, and that's actually the Golden Gate Bridge there. Interior mobile scanning is still fairly new. The accuracy levels on interior mobile are a lot less than static scanning. However, they're extremely fast at data capture. I would only recommend utilizing interior mobile for more of a mapping situation where you're doing schematic type studies, or you just need a quick lay of the land. Design grade data is a little more difficult to get with interior mobile, but this is kind of the next big arena, and I think you're going to see some big advancements coming forward. There's also airborne LiDAR, and airborne LiDAR can be basically scanning from an airplane or a helicopter. You can fly over an area and scan landscapes or cityscapes and get a tremendous amount of data rather quickly. Again, much lower level of detail and resolution on the scan data. So basically we're going to be focusing more on static scanning. And I want to go over with you guys today how this works. So we've got, say we want to scan this building facade. We would set up positions around the building. Here's our plan view of the building, and each of these represents a scanner location. And with all lasers, lasers are line of sight instruments. So in order to capture data, you have to be able to see what it is you're trying to capture. So that's why we would position ourselves walking our way around this building. Ideally, you want to have overlap in your scans between scan 1 and scan 2. These two scans over here don't have overlap, so I'd probably really drop another scan over here to get that overlap. So there's different ways that we stitch our scans together once we take them. And we call the stitching together of the scans registration. So in this case, probably the first method and the fastest and probably lowest level accuracy is targetless or cloud-to-cloud registration. And this method just basically, you pick elements on the building itself or on the object you're scanning to use to stitch your scans together. And what you're trying to do is pick a minimum of 3 points that are common from one scan to the next. And if you can see those 3 points and identify them in each scan, those scans will basically stitch together. There's also target-based registration. This we introduce our own targets. They could be a paper target. It could be a paddle target that you can rotate and flip these paddles back and forth and aim them at the scanner as you move the scanner around. Or they can be spheres. And spheres are great because no matter where you're at around the sphere, you always know where the center point is without having to run out and turn a paddle all the time. So spheres basically save the scan technician's time running back and forth turning paddles. But they're all suitable targets, and we use all of them. Now, I want to give you another example of registration. So we've got two scans here, the blue scan and the orange scan. And think of these little dots as our targets. So again, 3 targets that overlap from one scan to the other, and we can register these 2 scans together. So here's our blue scan. And one thing you'll notice, our scanner position is right here. There's shadows, and these shadows are being cast by, in this case, a column that is blocking the view of the scanner. So the scanner can see everything on this side of the column, but on the back side it can't see anything, so it casts a shadow. That's why we would have to reposition our scanner and take another scan. Here's our orange scan, so we're on the other side of those columns now, and we're capturing the data that the blue scan didn't capture. But both of these scans are not positioned in relation to each other, and that's what registration does. It basically takes these 2 scans and stitches them together in proper relationship to each other. And then you basically repeat the process through the rest of the area that you need to be, that you're interested in. Now, with any type of measurements, there's always a degree of error. And much like the gentleman on the first slide we looked at had a problem with error in his measurements, you can also get error in your scans. And you won't necessarily know it by looking at the scans. Sometimes it's evident, but other times it's not. and the error tends to accumulate as you take more scans. So what can we do about that? Well, let's look at this. Here's our first scan, scan 1 position. Take another scan. We stitch them together with those 3 targets. Take another scan, and the more of these you start to stitch together, the more the error accumulates, and these scans start to rotate and twist on you. So the way we prevent that from happening is we use survey control, and that's basically where we'll introduce a control point under one of our targets. And this is done by a traditional survey process. You can use nails, you can use other points, a scribe. If you're on the carpet, you can sometimes we just tape down a piece of paper and make an X on it, and that's a temporary control point. But use a total station laser such as this, shoots the prism, pole, which is on a pole that is on the control point. And then using the surveyor's coordinates, we can bring that together when we're registering our scans and basically pull our scans back up into their true position so they don't rotate. Not every job needs survey control. Some jobs will need it, some jobs won't. It adds more cost. So knowing when to use it, when not to use it, is real important. Let's see. Another thing that we like to do when we're scanning is, for quality purposes, we'll take additional shots with a total station on elements such as a building corner, just a single shot, and then when we register our scans together, we can compare with these control validation points. You know, did that single point land where we would expect it to? And if not, then we can tell we may have an error as well. So these are just additional things that we would do for quality assurance. Now, what we're looking at on the screen right now is a video of a building that was scanned, both inside and out. And all these scans have been registered together into a single unified point cloud. And again, this is all three-dimensional data. You can see we can rotate around this building. We can do a fly-through. It looks rather unclear. The data is kind of like a bad bitmap image, if you will. But really, we're not looking at all the points, and you can see a tremendous amount of detail in here. We got all the underside of the joists for this building because they were exposed. You can see things like, well, the ceiling has all been captured, the cabinets. It's just a tremendous amount of detail that's captured in 3D. Let this run a little bit, and you may even capture landscape and trees. So once the data is captured and registered together, you need to do something with it. So the first thing we like to do is lighten the data, as we'll remove any data that we're not concerned with. In this case, we're just concerned with the building, so we remove everything on the ground. And that lightens the data, because this data can get to be enormous in file size and make it more difficult to work with. But it is three-dimensional. We can start to slice and dice this however we want. We can cut building sections. We can focus on elevations. We can create just isolate a roof area. Again, a framing plan if we can see the framing members. Reflected ceiling plans, and a horizontal slice through the data is nothing more than simply a floor plan. This data is three-dimensional, but we can also produce 2D deliverables out of it as well. So what you produce is really up to you. and what your needs are for your project. So it can be a 2D AutoCAD, or it can be a 3D AutoCAD, or a 3D Revit. Just depends. All right, so now what I'd like to do is just walk you through some of the ways various people are using these. We'll start with architects. Scanning is really ideal for doing things like building elevations. Doing building elevations through a traditional means with like a tape measure or even a handheld laser can be challenging. Imagine trying to get up onto this clock tower and document what's up high. Got to somehow get up there. It represents a safety risk for whoever the surveyor is, and just the challenge of trying to do it accurately can be pretty difficult. Horizontal measurements going around the building are fairly easy. It's the vertical ones that are the challenge. This 2D elevation was drawn in AutoCAD, and it was all done by scans that were taken from down here at the grade level. And the scanner just reaches up and shoots everything. One of the other benefits of scanning is something we call orthogonal imagery, which is really pretty exciting. If you're looking for a way to document an elevation of a building, orthogonal imagery could be a great solution, especially if you've got a building with lots of ins and outs that could be very difficult to elevate, or if you're on a real tight budget. It takes time to generate line work in a traditional elevation. With an orthogonal image, you basically use the scanner to scan this building facade, and then you can create an image that's perfectly orthogonal. You drop that on a sheet. It's nothing more than a JPEG image, but it's perfectly to scale and perfectly orthogonal. So you can dimension to it. You can draw on top of it. If you want to augment some of the features with line work, you can do that. But you can imagine assembling a sheet of elevations just by dropping photo images on it that are to scale, as opposed to trying to draw all that or take still photos and stitch them together. You won't have to worry about parallax or any of the common problems with a traditional photographic approach. Scanning is being used heavily for historical preservation purposes. And you can see in this example, Union Station in Washington, D.C., the type of detail that the scanner can pick up. All of this, again, was taken from down at grade level and represents this column capital up here, which for scale purposes, it's maybe hard to see. These are people down here. So this is fairly high up in the air, and you can see the amount of detail that you're still able to capture. This can be then also processed into something like a 3D BIM using, in this case, we used Revit. Just some more examples of the type of deliverables you can get for your existing conditions. It's capable of incredibly complex geometries. And just for representing imagery within this space, it has all kinds of applications. Now I'll take you through another type of application. This was a project up in San Francisco where architect was looking at designing a new high-rise building in this location, and they needed to perform some shadow and line of sight studies for the city to get some preliminary approvals. What they needed to do is model the surrounding buildings as well as mock up their proposed building. The problem they had was they didn't have any data on these buildings, and as you can imagine, they they probably weren't going to get much cooperation from their neighbors if they went and asked if they had record drawings. The city also didn't have suitable record drawings for them. So what they decided to do is to use laser scanning. These red boxes represent areas where we had concerns about whether we'd be able to capture data. All the scans are going to be taken from the ground level up, and we didn't think we'd be able to see some of these elements on top of the buildings that would be important for these studies. Nonetheless, they decided to move forward with it, and this is the data that was captured. And all this data was captured over the course of, I would say, about 2.5 days. So it's a tremendous amount of data rather quickly. Survey control was used, so this was all set on a real-world coordinate. And because it's just a shadow study and a line-of-sight study, they weren't too concerned with filling in all the holes in the data. They just needed to represent things in more of a schematic format. Again, strip away the data that wasn't necessary, and you can see, yeah, we were missing the tops of some of these buildings. We did capture the top of this tall building because it was a barrel vault, and we were able to see it from back afar. The resulting model was nothing more than a massing model, but it was very suitable for the purpose that it was intended. To fill in the missing data on the rooftops, we actually were able to get our hands on some airborne LiDAR that was flown over the area and fill in the missing data that way. So these are all just different tools in the toolbox, and getting them to perform the task at hand. If any of you guys out there are fans of the rock band the Eagles, you may recognize this as the Hotel California on their famous album cover. This is actually a Beverly Hills hotel, and this facility was scanned primarily for the interior. The architect was doing interior renovations, and they had a challenge because each of these guest rooms was unique in some way. It wasn't your typical Marriott with standard rooms. So scanning was chosen to do the documentation. There was also some areas of fairly complex geometry, such as the grand staircase. And this is always nice to point out, you know, the scanner doesn't care how complicated the geometry is. If it can see it, it can capture it, and it can capture it in high detail. Modeling something like this gets to be more of a challenge with a tool that's, you know, like Revit in this case was an orthogonal type tool. Trying to model real world out of plumb conditions can be challenging, but it can be done, and this goes to show that. The lobby area was also fairly ornate and really had no straight lines in it. There were curves everywhere. Measuring this through a traditional means would be very challenging. I don't know how you would do this with a tape measure or even a handheld laser. In this case, they were also interested in features such as the crown moldings and the base moldings. So the scanning method was chosen because we could extract out things like the moldings. Simply by slicing through the point cloud, we get a profile, and we build that profile and bring it into Revit and turn it into a sweep, and we're basically modeling all the ornate moldings. Now, one thing I like to point out is a lot of times people are relying heavily on record drawings. And even in the case where we have a set of record drawings that we have a high level of confidence in, things don't always get built as they're designed. This is the Beverly Hills Hotel lobby, and after we scanned it, we decided to do an overlay check against the record drawings. And as you can see here, the line work that was generated from the scans is shown in red. In some cases, it's pretty spot on. As you work your way around, you can start to see some variance where the real-world conditions vary from the record drawings. In some cases, it's fairly dramatic. So even where we've got highly dimensioned, highly confident drawings, you can see where scanning can really be of benefit. I'll show you guys an animation real quick. See if this plays. All right. Unlike the other animation we looked at, this one has been colorized using real-world color. And that's done with an onboard camera on the scanner that captures photo imagery, and we map the photo imagery to the point cloud data. So it gives you a lot more realistic rendition of the data you capture. Now this was done for a quick presentation to the Building Enclosure Council, and we just needed some interesting facades to capture. So we went out, and this whole area was scanned in probably the course of about an hour, hour and a half. We didn't use targets. We were more concerned with just some quick imagery, and we went back and used a targetless registration process. And probably with about, I'd say maybe half a day in the office and less than 2 hours in the field, we were able to generate everything you see here, and, including this fly-through. So for quick visualizations, scanning can be a great tool. Now take a look at some methods that engineers are using this data for. And one of the biggest things that we see engineers use this for is above ceiling plenum scanning and modeling. And this is probably one of the most difficult things that we do, primarily because of access and getting the scanner to see everything that needs to be documented. We have to get the scanner up into the ceiling, so we either have to pop ceiling tiles or find access panels. The more we can get the ceiling open, the better. But even so, if you can get the scan head up into the ceiling, there's going to be an obstacle right in front of you usually, a pipe or a duct. You've got to get on the other side of those to capture more data. So if you only would need one scan down below the ceiling to capture the room, you might need 4 scans above the ceiling to capture the same space because of all the obstacles. But there's really no better way to capture complicated mechanical, plumbing, structural, electrical information. It's an example of a high school that was undergoing a upgrade for their mechanical equipment, and this is a theater building. They were going to locate some new equipment out in the parking lot and replace and upgrade the equipment in their existing mechanical room. This is a picture inside the mechanical room, and if you've ever had to document something like this, I think you probably just hope someone else was going to do it for you. But with scanning, it's fairly straightforward and simple and easy. All this geometry can be documented in a high level of detail. This mechanical room had a little mezzanine up above, and there were maybe about 8 scans, and we captured the whole space. The resulting model looked like this. And what's great about this is even with spaces that are highly congested and have lots of difficult geometry, such as all this piping and conduit, once it's modeled, you could then prefabricate and bring out new pipes and fit them right through this mess without having to worry that you're going to have collisions. So a lot of the contractors are really driving laser scanning and modeling as part of their process now as a result. Structural systems such as this, extremely complicated to document. With a scanner, it's really pretty straightforward and easy. In fact, this space is extremely easy because it's wide open. There's very few obstructions. A scanner will reach up and capture fine detail from these connections, even up high. You can see the rivets in this, and a lot of detail. All that can be modeled. In this case, it was modeled as a 3D AutoCAD. Contractors are using scanning and BIM because it basically gives them a chance to recreate things in advance of building them physically. And that saves them a lot of time and a lot of money in change orders. This project was a new ground-up building, and it was this model was created from record drawings so that the contractor could understand where clashes were going to take place in the design. Once the contractor started building the project, they had us go out and scan this, and they were using the scan data again as a comparison check against the model to see where things were being installed in reality versus what was modeled. What I like to point out with this is this is the bottom chord of one of the trusses that was modeled. And you can see the laser scan data here and how it fits to the bottom side of this, this truss. And there's actual camber built into the truss before it was fully loaded, and the scanner picks that up. So any real-world out-of-plumb conditions are going to show up in the scan data. A tool like Revit's going to want to draw this nice and straight, even though the actual joists are bent like this. Once that roof gets its load, it's going to flatten out and it's going to meet the design purpose. So if you're modeling from scan data, you're going to have to decide how you want to represent things. Are you going to try to model the real-world condition, or are you going to model a close approximation? These are all things that you don't generally have to deal with when you're doing what I'll call design BIM. Again, you can compare the model with the scan data using a product like Navisworks. Scanning's great for modeling rocks. I don't know how you would model a rock without a scan. But it's very good at capturing even the most organic shapes and creating a model from it. Products like Geomagic or Polyworks or 3D Reshaper can be used to model elements such as this. This is a Scan-to-BIM project of an existing building. Was laser scanned. They were turning it into a medical office building. And I'm going to show you just a quick section cut through this model. What I like to show about this is how contractors have gotten really savvy with their use of scanning and modeling. They've realized that the most expensive, time-consuming part of the Scan-to-BIM process is actually modeling. Scanning goes really quick, but you can spend a tremendous amount of time modeling things. So in this case, they said, you know what, we're not concerned with everything in the building, or we don't want to spend our time and money modeling everything. We're just going to model the building shell. We're going to model some of the structural elements, the columns. Some of the sprinkler mains were modeled, but not the branch lines. Don't worry about the stair. And instead, we'll just use the scan data where we we need to see where those things are, and if we're going to run things around those, we won't model it, we'll just work with the scan data. So kind of a hybrid approach that saves time and money, and I always recommend using the scan data to the greatest extent possible where you can. You can always come back and model more later and not have to go back out to the field to do it. This same building, they were concerned with the flatness of the floor slab. So what we were able to do is generate a floor map. We call this an image intensity map, and it basically shows a 3D map of the floor using color. Now the way this works is the different colors represent different heights of the floor slab, and we set a benchmark. Benchmark could be anywhere, really, and in this case we just called this 0.00, and it's a floor finish of 0 feet 0 inches. That's our benchmark. Our color legend over here shows a gradation of scale in color, and so each of these colors represents a 1/4 inch change in elevation. So going from red to the orange side of the spectrum, we're moving up in elevation, and going from red to the blue side of the color spectrum, we're going down in elevation. So looking at our floor slab here, we can start to see the red areas are close to our 0,0, and as we move across, we're going to the yellow side of the spectrum. So this is actually going up and undulating back down and up and down, and you can get a sense of what this floor slab is doing. We also shot this with a total station laser through a traditional survey process, and these are just random points kind of set up on a grid. And what was interesting about this particular project, we didn't know that the floor was doing this when we captured the data. So the total station shots were where these black dots are, and they just happened to land about in these red areas. So if you were going just with the points that the traditional survey captured, you wouldn't necessarily have a full picture of what the slab looked like. You'd think it was actually pretty flat. So the scan fills in a lot of the detail in between traditional survey points, and you can get a much clearer picture. You can also use this for things like reflected ceilings. In this case, the blue areas have some sag. They may want to go in and tighten up some ceiling wires. You can do this on a facade to see if the facade is has got deformation or is slanting one way or the other. Just a great use of scan data. I'm going to take a look at some 360 imagery now. One of the ways we create 360-degree imagery is through just a simple DSLR camera on a special bracket and a fisheye lens. We take a whole series of photos and stitch them together and create a panoramic image. From there, we take that panoramic image and we can turn it into, oops, hang on here, I got this. We can turn it into a 3D VR QuickTime image that you can rotate around in. You can zoom in and zoom out. See these valves up here. These are great. They're fairly simple to create. They're quick. They're easy. What I like about them that's different than the traditional photographic process, obviously, is I can look at what I want to look at. With a still photo like this, sure enough, I'll probably want what's just outside the frame of my photo. With these, I can just simply rotate around. This has nothing to do with scanning. This is purely a photographic process. The camera sits on a tripod, such as this, and these are great. They're quick, affordable. There's another form of 360-degree imagery, though, that goes hand in hand with laser scanners, and there's a couple different varieties of this. One of them is produced by Leica Geosystems, and they have a product called TrueViews. TrueViews work a lot like the 360 image we just saw on the screen. In fact, I'm going to pull up a live TrueView here. TrueViews work in your browser. So basically, you get a link and it goes to a map such as this. This is a boiler room that was scanned. And we had 3 scans in here. And the scan positions are represented by these yellow triangle icons. We call them scan worlds. Again, I'm just viewing this in my browser. This is a plug-in. You install the plug-in and then you get the TrueView link, and then when you click on these, the TrueView viewer pulls up, and this is a free viewer. And you can rotate around just like the QuickTime images we were looking at. But what's neat about the TrueView images, I'm going to zoom in on one of these concrete blocks. You'll notice at the top of the screen here there's some icons, some buttons. These are measure tools. You can mark up things right here on the TrueViews. But I'm going to pick a point here. I'm going to pick a point right about there. Now that's in feet. I'm going to switch over to inches. And we can see that's basically a 16-inch measurement. I'm going to pick this way. And TrueViews are, you can't snap to an edge with a TrueView. You're basically doing it by picking by line of sight. So if you need something more accurate than that, then you can go right into the point cloud data itself. But for quick visualization on site, it doesn't take a lot of time to learn how to use a TrueView, so you don't have to be technical. There's other tools in here too, and one of them I like is the kind of the vertical measure tool. If I wanted to know the underside of this surface, how high up it was, I could come in and take a measurement using this measure distance. I'm going to pick a point there, and pick a point here. And basically what I'm looking for is the Z value between those 2 points. And that Z value is represented right here. It's 9.722 feet. That's perfectly vertical, regardless of where I pick. I'm just going to exaggerate a little bit. That vertical distance difference is 9.746. So you can get some really good verticals out of TrueViews. What they're not necessarily good at is measuring around elements such as this pipe. Let's see, so I'm going to get out of TrueViews for a second. There's also something called Webshare, which is produced by Faro. It's another scanner manufacturer, and they have their own version of TrueViews. And this is also browser-based. The thing I like about Webshare is Webshare doesn't require any plugins, so you don't have to worry about installing anything on the client side. And I actually prefer this interface over the TrueViews. You can see the floor plan view here, and all these dots represent scan locations. You'll notice these dots all have different colors. Those relate to this color scale over here. So the lower, or the yellow color, is at a lower elevation, much like the image maps that we were looking at earlier, 7.5 feet. So it'd be one of these guys out here. This is 7.479 feet. As you move through the scene to the higher colors, this one is up at 14 feet. And these are all set on a real-world coordinate. I can click into this this scan and basically look around in here. It's a 360. You can see we're up on a loading dock here, so that's why we're up higher. I'm going to pop back out. Oops. Come back in here. Go back up to my map. And I'm going to come out here outside the building. This is actually a loading dock where they offload grain from ships. And you can see the ease of navigation, getting around the site fairly quickly. I can change my position. I can also do measurements inside of here as well. If I want to know, say, the width of this opening. Take a couple of quick points here. And it'll come back with a measurement. Takes a second in this. So there I've got 21.8 feet. Same thing, vertical measurements it'll do. I'm going to pick here, and I'm going to just pick over here. So that's a point-to-point measurement. That's not a true vertical. But if I click on this again, oops, there we go, it's going to give me that perfectly vertical dimension. So you can see not only the point-to-point measurement, but the true vertical. So it's just another type of tool that's available whenever you scan. And with that, I'm going to conclude with just make you guys aware of an organization out there, the U.S. Institute of Building Documentation, the USIBD. If you deal with existing conditions, you guys may want to check this out. It's a nonprofit membership organization dedicated solely to supporting all stakeholders with an interest in building documentation, whether you're an architect, owner, contractor, engineer, service provider. I encourage you to go check this organization out. They're developing standards and educational resources, putting on webinars and such like this one. So with that, I'm going to turn it back over for questions.
Thanks, John. We appreciate it. And as you said, okay, we've got time for a few minutes. We have a few minutes left for some remaining questions. And John, you should have a few of those questions in front of you, so please feel free to respond at will.
Let's see if I can see the questions here. Hang on, hang with me 1 second. Okay, there we go. Oh, well, there's one. I can't hear you. Sorry about that. I'll try and talk louder. Hopefully you could have heard some of that. Let's see, can TrueView work with Faro or only with Leica? And the answer to that is no, TrueView can work with both Faro data and Leica data. If you scan with a Faro scanner, you just have to convert your data to a PTS format, and then you can publish TrueViews. Let's see, another question. Can you give us a taste of how the point cloud to Revit model transition occurs? Can it be automated at all? If so, how successful is this? Yeah, automation is something that is very much needed. There is some automation. There's a program out there called ClearEdge, and you may want to check that out. They've got some automated feature extraction for specifically for, well, they have a building product. So for putting things that are maybe repetitive like windows, they can do feature extraction into Revit. They also have pipes and ducts that are fairly automated, but there is a cleanup process to it. It's not perfect, but it certainly can save time. Let's see, what else do we have? For a not commercial, smaller scale firm, it makes more sense to hire another company to do this. Is there a website where these companies are listed? That's a good question. Yeah, this is a good service to outsource. There's a lot of companies out there that provide this service. As far as a website, you can probably just do a Google search and find a lot of them. I don't know of a website with a listing. The USIBD website would be good to check out. If you get involved with that organization, there's a lot of service providers in that organization that you'd be able to network with. I know they are looking at building a directory of service providers, but that's not yet available. You can also check out, there's an industry conference called SPAR, S-P-A-R, put on by a SparPoint Group, and I think this coming year it's going to be in Houston, Texas. SPAR is probably the best place to go to get engaged in the 3D laser scanning world. It's got tremendous resources there, lots of exhibitors. You can learn a lot real quick. I encourage you to go to that conference. Have you been able to scan with drones? Well, drones and scanning are fairly new, and there's a lot of people working to do scanning with drones. I've seen scanners mounted to a drone and flown around a building. There's one that you guys can check out, maybe Google Scan-copter, and it's pretty impressive. It uses a total station to track the scanner as it's flying on the drone, and that was showcased last year at the Faro conference in Orlando. I don't know how accurate it is. There's also people mounting GoPro cameras to the bottom of drones and using more of a photogrammetry process and tools like Autodesk Recap. Recap can also help create point clouds out of photo imagery. However, the accuracies are a lot lower. It's not going to come close to matching a static scan. So they may be good for visualization at this stage. I would guess less applicable for design grade data. Have you had any multi-family building scans? Yes. We actually have. We've scanned all kinds of projects, really. Do you process a 3D scan into BIM for historic preservation, for example? Or how do you process a 3D scan into BIM? Do you draw over the top of it? Yeah, what we do is we bring the scan data right into Revit, and then you basically think of it as kind of using these points to snap to and use your standard Revit tool sets to draw with. The challenge that you're going to face if you start working with point cloud data is the file size is enormous. You're going to want to have some good machines to work with. You're also it's going to take a while to train your eye to interpret point cloud data, usually. Maybe less so on the architectural side, but on the MEP side, it can be very challenging, especially at first, because you can see through the point cloud data, and oftentimes you don't really know whether you're picking on a point in the foreground or in the background. It can be challenging, especially if the point cloud data comes in monochromatic and there's no color. Then it gets difficult to read. Let's see. Another comment on not being able to hear. Robert, can you hear me okay?
Yeah, you've been fine right here with me, absolutely.
Okay. I don't have a way to turn up the volume anymore, so hopefully it's coming through. Volume. I just keep seeing volume questions. Gosh, I'm sorry, guys. What's the average cost of running a scan in a single-family residence? Well, I would, let me give you some kind of rules of thumb. Scanning, what you could expect for cost, usually we quote it in day rates. You know, how much does it cost to have a crew out on site scanning for a day, and the prices are going to vary around the country. You could probably expect, if it's just a single guy going out with a scanner, it might be $1,200, $1,500 a day. If you got a crew going out, you're probably $1,800 to $2,000, $2,500 a day. It's really going to vary. Depends on what equipment people are using. To scan a multi-family building or a single-family residence, well, let me go back to days. How many scans can you get done in a day? We can get done probably, depending on the scene, anywhere from, say, 40 to 90 scans done in a very long day. It really depends on your lines of sight and what kind of obstacles you're dealing with. If I have a 100,000 square foot warehouse space that's wide open, it may take me a handful of scans to get the whole inside of that space. If I have a 100,000 square foot office building, it could take a couple hundred scans to get the inside of that space. You can do the math as far as how many scans per day, and then you convert that into what the day rate is, and then you can start to come up with some numbers of what this costs. Let's see, I don't see any other questions in the list. Does anyone else have any other questions?
Well, we are just about wrapping up right at the 1:30 mark, so why don't we think about wrapping right now? John, I want to thank you, certainly want to thank you for your presentation and participation today. And as far as our audience is concerned, we just hope that you guys have found this to be an informative session and hopefully of some benefit to you. Moving forward, should you have any questions or require further information on what was presented today, please feel free to reach out directly to me via email. And my address is rblum@asti.com. That's rblum@asti.com. And I'll be happy to assist you with anything relative to the presentation today that you might require. And that concludes it. This concludes today's presentation. We want to thank you for your time and participation. We again encourage you guys to visit the Live Lab Learning site for details on our next webinar and series, and hope to see you then and there. And I think that concludes it. So our appreciation to one and all, and have a good afternoon, everybody. Thank you.